Good day, I'm Norman Wahlberger. In this video, we want to talk about this fundamental symmetry that we've introduced into mathematics. So the usual world of mathematical objects is now augmented by a kind of alternate mirrored world of anti-objects. And formally, this is done very simply by just putting bars over objects to denote the anti of an object. And this is going to be crucial for us in allowing us to use the multiset framework to introduce negative multiplicities in a real sense, in a concrete sense, rather than just formally and just sort of waving our hands. So we actually have objects that represent -3 cows, or more typically -3 pixels, or -3 singletons, or -3 of some particular mathematical object. It's going to be very important for us when we want to do abstract algebra and look at spaces, linear spaces, groups, rings, fields in our next video. Okay, so the basic idea is here are our familiar kinds of objects that we might want to use in mathematics, and here are the corresponding anti-objects, which are just created by taking these objects and putting bars over them. We're just following the physicists' usage here. So here's the number 3, here's anti-3, or 3 bar. And we just take the actual object and put a bar over the whole thing. And if we want to save space, or it's a little bit hard for us to put the bar over it, we'll put the bar on the right-hand upper corner. Here's our -4 number. Here's the anti of that. -4 bar is just to take the object itself, which is actually a bunch of anti-marks, and put a bar over it. Here's a vexel, which is an mset of singletons. Here's the anti-object, v bar. Here's an ordered set, S. It's got some different elements. It's ordered because we see some commas. Here's the corresponding anti-object. We just take the whole thing, put a bar over it. We don't modify it in any way. We just put a bar over the whole thing. Here's a maxel consisting of a bunch of pixels. Here's the anti of that maxel, m bar. Just take the whole thing, put a bar over it. So we have this fundamental symmetry, which is really officially introduced by this little equation, that anti-mark times some object heart, whatever that might be, as long as it's an actual specific object that we've already nailed down, then this product is going to be what we call heart bar, or the anti-heart. And the crucial defining property of this anti-object is that if it and the original object reside in an mset together, then they cancel. That means they both disappear and they're replaced with nothing. So this is not really a multiplication of heart times heart bar. This is just to denote that if we have a heart and an anti-heart together in the same mset, then they are going to cancel. And notice that it's crucial for us that we do have a notion of nothing as being represented by a blank part of our page here to express what happens when we combine these two things. So in today's video, we want to talk a little bit more about this symmetry, get a little bit more experience with it, and then move to seeing how it actually helps us in setting up a wider theory of vexels and maxels. Now, to get a full symmetry between objects and anti-objects, we're going to want that the anti of an anti-object is the original object. So we're going to introduce that as a definition. We're going to say that when we take the anti of an anti, we get the original. In other words, if we take anti-mark times heart bar, which is the anti of the anti-heart, there's the heart, there's the anti of it, and there's the anti of the anti. We want that to be the same as the original object heart. So we're going to introduce this as a definition. And this is really consistent with our understanding that anti-mark times anti-mark is mark. Because this thing here is anti-mark times heart bar, and this heart bar is anti-mark times heart. And what we're doing is we're saying, let's agree that this thing is the same as this. And we're allowed to use associativity at this level to rewrite this as anti-mark times heart. In which case we would get mark times heart, which we know is heart. So the equality of this and this is really equivalent to this associativity that we're allowing ourselves at the level of multiplication of anti-marks with objects. Okay, now we can introduce the idea of the negative or negation of an mset. This is a very powerful thing to be able to do. Okay, so we are now allowed to talk about an mset and its negative. How do we do that? Well, here's the definition in a kind of abstract example. So if here is an mset, say heart, heart, diamond, and these are some kind of mathematical objects that we have agreed that we've already clearly defined. Then the negative of this mset, which is what we get when we multiply by -1, here is the number -1. Then the way we multiply msets is, what we should do is we should take the entries of this mset and the entries of this mset and take all possible products. So anti-mark times heart, well, that's heart bar. Anti-mark times this heart, that's heart bar. Anti-mark times this diamond, that's diamond bar. So the effect of multiplying by -1 is to take the anti of each of the original elements of the mset. Go from mset m to the mset of its antis. And that is the negative of the original mset. So negating an mset means taking the anti of all its entries. So we don't have to do this now in a formal sense, really. We have a rather specific idea and framework for talking about combinations of msets, including negative combinations. Right, so we can do things like now, not just add the mset A plus the mset B. We can also take the mset A minus the mset B. And we have a meaning to what that means. So here are some exercises for you to ponder, to practice your understanding of how these anti-objects interact with ordinary objects. So try to simplify these expressions if you can. It might not be possible, so some of these expressions might not actually make sense. So you have to try to decide which ones do. So here, for example, is well, it's actually a singleton because it has a singleton 1 in it. And here is another kind of object which has a singleton 1 bar in it. And we want to add those. Does that make sense? And if so, what do we get? Here we have number 2, singleton 2, and here we have the anti of the singleton 2, which is subtly different from this situation here. What happens there? Here is the anti of mset with inside 3 bar. Here we have this mset plus this mset. Here we have the negation of this mset, where this one here contains a singleton 4 and the anti of the singleton 5. Here we're adding the anti of the singleton 6 and the anti of the singleton 7. Here we have an mset consisting of numbers 0, 0, 1. And here's an mset consisting of integers 1, -2, and also the anti-0. And here's a difference of 2 msets. So maybe we can also introduce some notational convention if we have to write this anti kind of object in a typing kind of situation. Perhaps we could introduce the idea that, say, the pixel 1, 3 anti, or the 1, 3 bar, we could write it perhaps like this: anti of pixel 1, 3. That's pretty unambiguous. Or maybe we could write pixel 1, 3 and then put a bar behind it, meaning this object barred. Okay, so we could use bar or anti possibly to convey this in a typed situation. So here's some little things to think about. So one of the main things that we want to do with these anti-objects is allow us to be a little bit more flexible about the use of msets. We want to enlarge our notion of msets now to include, as we've seen, not just objects, but also anti-objects. And so we want to introduce a bit of terminology that captures that idea. So let's talk about an integral mset or an imset. Okay, so this is some kind of variant or slight generalization of an mset, an imset. And what is an integral mset? Well, suppose that we have a notion of mset of some type. So we've decided on msets whose elements are of a certain type, and we have a very clear idea of what we're talking about in that context. Then we'll consider imsets of that type to be, well, a more general kind of multiset that allows not just the objects of the type that we're considering, but also their antis. All right, so that objects of the type we're considering, as well as anti-objects of that type. So when we allow both objects and anti-objects of a given type, we'll talk about that as being an integral mset, or short, an imset of that type. So here's a very important illustration of that. It's going to play a big role for us. The idea of an integral vexille. So we've already talked about vexels in the context of msets of singletons from, say, Nat. Where, for example, here is a vexille, which has some singletons, and the singletons are from natural numbers. There's a singleton 0, the singleton 1, singleton 1, singleton 3. That's a vexille. And we've seen that we can represent that vexille geometrically or visually with this frieze-like object, where we record the number of 0 singletons in the special little box at the beginning. There's one of them. And then record the number of 1 singletons, the number of 2 singletons, there aren't any, and the number of 3 singletons. And this is an open-ended kind of thing. The box doesn't really end. It's possible for there to be further additions. And then we saw that we could extend that idea. Once we have integers as well as natural numbers, we can think about using the integers to specify an extended labeling structure. All right? So we had vexels from integers. These are msets of singletons from int. That means something like this, where we have singletons whose entries are not just natural numbers, but also possibly negative numbers. So over the full range of integers. And representing something like this involved a similar kind of thing, but now we're allowed to introduce multiplicities of the negatively labeled singletons. So here we have a singleton minus 2. There's one of them, so we put a 1 in the minus 2 spot. There's 2 minus 1 singletons, so we put a 2 in the minus 1 spot. There's 0, 0 singletons, so this special box has a 0. There's 0, 1 singletons, and there's a single 2 singleton. So we've used integers here crucially in extending our vexille or vector point of view from a one-sided story to a two-sided story. That was important. And now we're going another step up, okay? So now we want to consider integer vexils or integral vexils, and let's do that in 2 stages. So first of all, from Nat, where we consider imsets of singletons from Nat. Means we're back in this situation here, but now we're allowed to use not just singletons, but also anti-singletons. Okay, so here we have a singleton 0, and here's an anti-singleton 1, and a singleton 2. The 2 singleton 0s are represented by this 2 in the 0 labeled box. The anti-singleton 1 is represented by this minus 1. Right? So this minus 1 now is telling us that instead of having 1 singleton 1, we have minus 1 singleton 1s, which is the same for us as having a single anti-singleton 1. So an anti-singleton 1 is playing the role of minus 1 singleton 1s. And that singleton 2 is represented by that 1 there. So the novelty now is that we're allowed to put integers here, including negative numbers. And the negative numbers that appear here are just a reflection of the existence of anti-singletons in the actual vexel that we're considering. And here's the more general thing, an integral vexille from integers. Here we have a vexil which contains singletons both with natural number entries and also with negative number entries. But we also have anti-singletons. So in this case, what do we have? We have -1 singleton with an anti and -1 singleton with an anti. So there's -2 things altogether in the -1 box. There's the 0 box, there's the -1 box, there's -2 -1 singletons. There's a 0 singletons, there's a single 1 singleton, and in terms of singleton 2's, there's -1 of them because there's a bar over here. So here we're using integers in two distinctly different ways. We're using integers, first of all, to allow ourselves to index an entire two-sided array of positions. Position 0, position 1, position 2, as well as position -1, position -2, position -3, and so on. But we're also using integers to represent negative multiplicities, like negative cows, -3 cows. What does -3 cows mean? Well, we now know, in the mathematical context at least, what it means. It's like there's 3 anti-cows in our mset. Of course, we're not dealing with cows. We're dealing with lists and sets, and multisets, and ordered sets, these data type structures. And for us, the anti-object is just what you get by formally putting a bar over the object. So to summarize, we've now identified a new framework for vectors. Integral vectors from integers. So these are imsets of singletons from int. This is going to be our preferred overarching domain for doing vector arithmetic. In other words, for doing linear algebra, in fact, for doing geometry. It's a very nice framework, but now we know exactly what we're talking about here. At some point, we may actually go a little bit further and up this a little bit to not just having integer entries in our vexels, like in other words, when we write down a vector, not just having integer entries, but also having rational number entries. So once we get to the stage of having an official version of rational numbers. But currently this is a very powerful framework. So typically what we're talking about is something that looks like this when we represent it geometrically. There's a frieze, it's two-sided, going to the left and right. There's the special 0 position, and the actual entries now are integers, representing multiplicities of singletons, where the plus signs would correspond to having honest singletons, and the negative signs would correspond to having anti-singletons. And necessarily these things are finite because we are, I remind you, always obliged to write things down fully. When we're talking about things precisely and completely, we have to illustrate our concepts by writing things down completely and precisely. So no going off to infinity at this stage. Okay, so an actual object of this has to be written down entry by entry by entry, all of it there. And it's really a short form for a corresponding mset or imset. So these are two-sided open-ended vectors with integral entries, and they correspond to imsets of singletons from int. We're going to say this is a lovely framework for thinking about geometry and linear algebra in a very big way. And another main example for us are integral maxels. So we started off talking about maxels as msets of pixels from natural numbers, and then we enlarged that to consider maxels as msets of pixels from integers. For example, here's a maxel with these 3 pixels, 0, -1, 0, -1, 1, 2. And that corresponds to this geometric grid kind of view where this is the 0, 0 position. The 1, 0, 2, 0, 3, 0. Over here is 0, 0, 0, 0, 1, 0, 2, 0, 3. But now also 0, minus 1, 0, minus 2. So this 2 here is representing the fact that we have 2, 0, minus 1 pixels. And there's a single 1, 2 pixel. Okay, now we want to extend this by going to integral maxels. First of all, integral maxels nat. These would be imsets of pixels from natural numbers. Just the same kind of sort of limited freeze that just works with a quadrant. But more interestingly, integral maxels from int. So these are imsets of pixels from integers. So these are just like these ones, except now we're also allowed the possibility of having anti-pixels as well as pixels. So here's n, which looks quite a bit like this one, except that instead of having these 2 pixels, it has their corresponding anti-pixels. So instead of having a 2 in this position, in this 0, minus 1 position, we have a minus 2 because there's these 2 anti-pixels. And we still have a single honest pixel, 1, 2, represented by that 1 there. So now we're in a position to deal with matrices with integer values. And matrices which are very general, that they have entries covering the entire plane. It's a very general, beautiful framework for doing matrix theory and linear algebra and other things as well, as we'll see. Okay. So we're now in a great position because these integral points of view, these integral msets that we now have at our disposal, allow us an entry to a lot of abstract algebra. So we're able to now, in a more precise fashion than we currently have, start talking about abstract algebra notions such as groups, rings, fields, vector spaces, modules, and other things in a more precise, careful, concrete manner. And next video I want to start that by giving an overview of abstract algebra, a bird's eye picture of abstract algebra. It's relatively modern mathematical development, roughly 100 years old, and which is now very, very extensive, but I want to give you an introduction to this, and then we'll be in a good position to start using this concrete, precise way of thinking about data structures to revitalize many of those topics. Very exciting. So I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.